So last time, what were we talking about? Yeah. What about probability density? Yep, we made graphs. Shall we remake those graphs real quickly? I think it's a good idea too. We plotted the wave function of a 1D particle in a box for the ground state, first excited state, and second excited state. What's the value of n for the second excited state? Yep. And then what else did we plot? Yep. The wave function squared. What does the wave function squared tell us? Yep, tells us the probability. If we look at the absolute value of that squared, what is the magnitude always going to be? Yeah. Two squared. Okay, let's plot these things. For psi of 1, what does the wave function look like? Yep. Not very exciting. That was meant to be symmetric. Do we catch the whole periodicity of the sine function with this guy? No, that's like the first half, right? Okay. What would the electron density look like? Yeah, same thing. Because it's just that squared. I was improper. Where should we be going to? Yeah, 0 to A in all of these things. Okay, what about for the first excited state? What should it look like? You have a node. I liked the Navy SEAL hand signals in the back. That's how I communicate. I realize I am like a very person who likes to talk with their hands because my kids are starting to talk with their hands. It's pretty bad. Ellen, you said you know where the node is, right? Where's that node? Yep. And what is a node? Yes. And the wave function's value is what? 0. So like when you're thinking about it like in inorganic or in your other classes, that's really what we're talking about. When we shade an orbital, do you guys understand the connection of like this plot to that shading? Like what does a p orbital really mean when I do that? And how does it connect to this picture? Yep, where's the node in this guy? Yep. So that's the node, and let's pretend the shaded in region is positive. We're talking about that there. Does that make more sense? Okay. Wave function squared, what's it going to look like? Oops, meant to be symmetrical. Yep, McDonald's M. I'm excited when we go to Finland. I'm going to McDonald's. Check it out. What's this part right here, though? Yep, a node. So what's strange about that? So the particle is moving back and forth, right? Does it ever exist in the middle of the box? Okay, for the second excited state, it's going beep, boop, back and forth, but it's never in the middle of the box. How does it go from here to here? It does. It never is in the dead center, though. No matter how many times you look in the center of that box, you're never going to see it in the middle. Okay. Wave function number 3. How's that one look? I didn't look in the back to see the Navy SEAL hand signals, Dar. I can't either. It's like, yeah. That's why I have a board to describe it to you guys. Okay, how many nodes? 2. Yeah. Some people might consider it 3 from the ends, but that's fine. Okay, what does the probability distribution function, or excuse me, what does the probability look like? Yep. Okay, I'm exaggerating this a little bit. What do you notice about the height of these like humps here? No, they should not be the same. They're decreasing ever slightly. And then these points are our nodes. Okay, then I asked the question, what happens if we go to a really big value of n? So what's the wave function going to look like? Yeah, really tiny, up, down, up, down, up, down, and a lot of wiggles in there, right? And then what will the probability look like? Yeah. Okay. So we described that a little bit. How probable is it to find the particle in the box over here compared to over here? How? Yep, it's the same. It's the same probability to find the particle throughout the box. That's kind of intuitive for what we know, right? We put a marble in a box, we shake it, and we open it up, and yeah, it has equal probability to be anywhere in that box. These systems are where the weird part happens. That doesn't seem very intuitive. Like, okay, you have an excited quantum particle and you zip it through the box. No matter how many times you look in there, you'll never find it in the center. Here, you'll never find it at these points, ever. Doesn't seem very intuitive. So what this means is it's equally probable to find the particle throughout the box. And that's similar to classical mechanics or physics. And when we reach that point, that's what's known as the classical limit or the correspondence limit. Where basically quantum mechanics behaves like classical physics. And through this, we get kind of a continuum of states. It's not really quantized states, but a large range of states. Okay, so that has to deal with the wave functions and the probability, but what about the energy? So if we take our wave function out to this correspondence limit, how does that impact the energy? Because if you look at some of the energy expressions, it doesn't seem really realistic to say, like, hey, if I look, my energy is just going to continually go up. So how do we deal with that? So next question, what about energy? So we derived an energy expression for a particle in a box. What was that again? H bar squared, n squared, pi squared. Did we do that? Or did we have, am I screwing something up with an H bar? Okay. All right. So what does this say? As the value of n increases, what happens to our energy? Okay, this doesn't look like a continuum. Or at least it doesn't really look that way. But what we need to do is consider changes in energy level. So let's consider the spacing. Between two adjacent energy levels. And normalize it. So basically what we want is an energetic expression to look at the difference between the two, and then we're going to divide, if we want to normalize it, based upon that value of n. Now, what is the value of n? Can really be anything we want it to be. For now, before we plug in infinity, or a value close to infinity, let's just evaluate it as is. Let's plug in some stuff in here, okay? The first term, what's it going to be? Yep. And notice the n plus 1 squared like that. Pi squared, oops. All better now. Minus h bar squared n pi. And then we're going to divide by this thing. Okay. A lot of repeat junk in here. What can we get rid of? H bar is gone. That whole thing's gone, except I left a square off of that. Anything else? Yeah. Okay, so now what we have left over is n plus 1 squared minus n divided by n, right? Okay, what next? Yeah, expand that guy. What's the, if we expand it, what's the value of it going to be? They should be. Good catch. Uh-huh. Yep. Okay, simplify that a bit further. Yep. Okay, so if we look at the difference in energy between two close energetic states, that's what we get. Now, let's consider this as we go to infinity. So, as n approaches infinity, what's going to happen here? Yeah, the bottom gets bigger faster than the top. They're still both infinite, but which one's a larger infinity? The bottom one? Okay. So what does that mean that this thing will approach? Really small? Give me a really small number. Yeah. It's going to end up going to 0. So the difference in the energy gets really, really small. Therefore, if you consider changes in that energy, the energy is a continuous spectrum. So even though it looks like the energy just keeps growing and growing and growing, it does keep growing, but the difference in it doesn't change very much. You hit a point where you just hit an upper limit and you just sort of hang there. Okay. So are there any questions about that? It's kind of weird to think that all the physics that you learn could be explained through quantum, but we just don't, because who wants to do integrals all the time?